sklearntreeexportgraphviz. Description: the exportgraphviz function from sklearntree provides a way to visualize decision trees trained using scikit-learn. It generates a graph representation of the decision tree, which can be used to create visualizations and understand the decision-making process. Inputs: decision tree. The trained decision tree model object from scikit-learn, such as decision tree classifier or decision tree regressor. This object contains all the information about the tree structure, including node splits, features used, and prediction outcomes. Output file optional: the path to the file where the graphviz representation of the tree will be saved. If not specified, the graphviz code will be printed to the console. Outputs: graphviz code. The function generates a string containing the graphviz.language code that represents the decision tree. This code can be used to visualize the tree using graphviz or other tools that can interpret .language. Visualized tree optional if an output file is specified. The generated graphviz code is saved to that file. You can then use graphviz tools like to generate a visualization of the tree in formats like PDF, PNG, or SVG. Steps: tree traversal. The function traverses the decision tree structure, recursively visiting each node. Node information gathering for each node. It extracts relevant information, such as feature used for splitting if applicable, split threshold or value, class or value predicted at the node, sample count at the node, impurity measure e.g. Gini impurity for classification. Graphviz code generation based on the extracted information. The function constructs the graphviz.code representing the tree structure. This code defines nodes, edges, and labels for each part of the tree. Metrics: Gini impurity for classification trees. The Gini impurity measures the randomness or uncertainty in the distribution of classes at a node. Lower Gini impurity indicates a more homogeneous node. Entropy: another impurity measure for classification. Entropy quantifies the disorder or randomness in the class distribution. Mean squared error (MSE) for regression trees. MSE measures the average squared difference between predicted values and actual values. Mean absolute error may similar to MSE but uses absolute differences, making it less sensitive to outliers. Visualization plots. Decision tree visualization. The generated graphviz code can be used to create a visual representation of the tree, showing the splitting rules, features used, and predicted outcomes. Fine-tune parameters. Feature names. Providing the names of the features used in the tree can improve the readability of the visualization, making it easier to understand which features are driving the decisions. Class names for classification. Specifying the names of the classes can enhance visualization by making the labels clearer and more informative. Filled when set to true. The nodes in the visualization are colored based on their impurity or other metrics, providing visual cues about the homogeneity or randomness at each node. Rounded. This parameter determines whether the nodes in the visualization are displayed with rounded corners. Uncertainty methods. Confidence intervals for probabilistic models. Confidence intervals can be displayed on the nodes to indicate the uncertainty in the predictions. Prediction probabilities for classification models. Probabilities associated with each class can be visualized on the nodes, showing the likelihood of a particular class prediction. Challenges and fixes. Challenge 1: overfitting. If the decision tree is too complex, it might overfit the training data, resulting in poor performance on unseen data. Sample use case: a decision tree with many nodes and deep levels, trained on a small dataset. might memorize the training data too well and fail to generalize to new data. Fixes to challenge 1. Pruning. Limit the depth of the tree. Minimum samples per leaf, or minimum samples per split to prevent overfitting. Regularization. Use techniques like L1 or L2 regularization to penalize complexity and encourage simpler trees. Cross-validation. Use cross-validation to evaluate the model's performance on unseen data and choose the best hyperparameters. Challenge 2. Difficult to interpret trees. Very large and complex decision trees can be challenging to interpret visually, making it difficult to understand the decision logic. Sample use case. A decision tree with hundreds of nodes and deep levels might be hard to interpret visually, even with a well-formatted visualization. Fixes to challenge 2. Simplification. Use techniques like pruning to reduce the size and complexity of the tree. Feature importance. Examine the feature importance scores provided by the model to identify the most influential features. Partial dependence plots. Use partial dependence plots to visualize the relationship between specific features and the prediction. SHAPS. Happily additive explanations. SHAP values provide a way to explain the contribution of each feature to the prediction.